Great. Yeah, so thanks for coming to the second part of my talk. And so, yeah, so I'm going to talk about some minimal surfaces and variable curvature stuff for a little bit. Then I'll talk about area and scalar curvature at the end. So to return to the question that I ended with last time, whether there's a variable curvature analog of this Random-Shaw theorem, there is, and so I'll kind of say the results that explain the results I proved in that direction. Right, so if we just, instead of taking the hyperbolic metric, take some other negatively curved metric on M, and so I'll say more about what this negatively curved metric is, or the conditions are that are on it. But what we're able to do is, what I'm able to do is to construct a foliation which we'll call f sub g of the Gaussian bundle of tangent two planes to M. Kind of thinking of like the metric G in the background, although as like a topological space, this doesn't make any difference. But so right, so this is like, you should think of this as being like the initial foliation F that it's kind of like the model case that I talked about last time. But these leaves are instead of being lifts of totally geodesic planes, since in general we won't have those, are lifts of minimal planes in MG. Okay, so instead we have minimal surfaces instead of are kind of playing the role of totally geodesics for totally geodesic planes for these foliations. And moreover, so these kind of foliations are conjugate to the model foliation in the sense that we have these maps, conjugating maps that send leaves of F, which is the constant curvature foliation, to leaves of FG. Okay. And then the construction of these foliations, so sort of how I want to think about this is we have the hyperbolic metric and we sort of start deforming off of it. It's like a one parameter family of metrics. Right. And so the question is, how long does this construction, or how long do these foliations continue to exist, since they certainly exist with the hyperbolic metric? It continues to work as long as the second fundamental form, called A, so we have A squared, is smaller than the ambient Ricci curvature pointwise at every point P, right? So I'll say this is like the second fundamental form at P, so I haven't said of what yet, but P. The surface pi. Where pi is a minimal plane, is any minimal plane that's like a leave of F. So right, so all of the leaves of, or sorry, F sub G are just going to be lifts of these minimal planes pi. Sorry, that lifts to F sub G. Okay, so the condition is that, so we have all these like minimal planes. When we lift them tangentially, they give us this foliation. And the condition that lets us, sorry, this should be squared. that lets us construct the foliations is that like the sum of the squares of the principal curvatures has to be smaller in absolute value than the ambient reaching curvature. So as long as our kind of principal curvatures are smaller than the sum of the squares of the principal curvatures, so kind of our like the intrinsic geometry of the surfaces, that's kind of controlled by the the ambient geometry, the ambient curvature, then we're fine. So kind of this condition is pointwise over all the different leaves. And so of course, starting out, we just have like the Ricci curvature of the hyperbolic metric is just 2, right, in absolute value, which is -2, so absolute value was 2. And then we have these totally geodesic planes, so their principal curvatures are 0. And then so kind of, yeah, so starting out, of course, like 2 is bigger than 0. That's like kind of the start condition, but then the second fundamental formula will get larger, and the Ricci curvature will also be kind of changing. So yeah, but this condition will continue to hold in kind of some neighborhood of the hyperbolic metric. So I guess the way to think about this is it's sort of like better than just kind of like, I don't know, some like non-constructively small epsilon that you can deform off the hyperbolic metric, right? So it's like kind of some, I think this is being kind of like more substantial neighborhood than that, but certainly not like the whole space of negatively curved metrics. And so I even construct negatively curved metrics on some closed hyperbolic three manifolds for which you can't have these foliations, right? So these foliations are kind of like, I mean, one of the reasons I thought to try to construct them is it's kind of like that they should be like a higher dimensional version of geodesic flow, right? So geodesic flow is like just one-dimensional geodesics, which are one-dimensional minimal surfaces. So we try to do this for like higher dimensional minimal surfaces. And you have this nice like constant curvature model case that you can deform off of and construct these kind of foliations that are like a higher dimensional version of geodesic flow for some negatively curved metrics, but eventually the construction breaks down. So there kind of isn't this perfect analogy to between geodesic flow and like these foliations, which yeah, but yeah, so why we do this? So so one corollary of this is that you can prove density results for closed minimal surfaces in the same way, like similar to what you have for geodesics, right? You know, negative curvature, closed geodesics are dense. You can say much more. So yeah, so these closed minimal surfaces are dense in metrics on your hyperbolic three manifold. Which admit these foliations. F sheet. Okay. Right. So you're able to kind of transfer information from constant curvature to variable negative curvature using these foliations and the fact that you have the conjugating map taking constant curvature foliation to the variable negative curvature one. So you can sort of move information that comes from homogeneous dynamics to variable negative curvature. And then, yeah, to connect to like on the previous part of the talk, so yes, kind of an important like source of inspiration for this, like why you think to impose this curvature condition is, so I mean, if you think back to the kind of the first part of the talk with almost Fuchsian manifolds, kind of the condition you did there was like having, if you have a minimal surface with principal curvatures smaller than the ambient curvatures, then that gives you a lot of control and lets you prove a lot. And so this is kind of trying to make that idea work in variable negative curvature. I was able to kind of come up with, or I was led to this condition where, yeah, having kind of principal curvatures controlled by the ambient curvature lets you kind of say a lot. And I'll just like end this part with a question, like it'd be for kind of Uhlenbeck's work that I talked about. There's this way of parameterizing the hyperbolic metrics by just kind of information associated to the minimal surface in the middle, the unique minimal surface in the middle, and kind of this almost Fuchsian region of quasi-Fuchsian space. And yeah, so it'd be great to if you could parameterize negatively curved metrics by, say, like, I don't know, the conformal class of the induced metric on exfoliation, and then maybe like information related to the fundamental form, second fundamental form. But yeah, but that would be kind of parameterizing an infinite dimensional space of metrics. So it would be much more complicated if it's even kind of possible to do that, I would imagine. But yeah, I'll just end with that question. And right, and so moving to the second part of the talk. So I want to talk about this minimal surface entropy that Collier Marcus Neves introduced in a recent paper, and that is why kind of, I mean, like this corollary that I proved, it kind of is a natural question based on, or like answers a natural question that kind of arises in the work that they do with their minimal surface entropy, kind of that's related to this analogy between geodesics and minimal surfaces that I said a little bit about. So, so if we have this set S epsilon of M of homotopy classes of pi1 injective surfaces with that'll say that are epsilon close to being totally geodesic. So I don't really say what that means. It doesn't matter that much for this talk, but you can think about just like they have you could, one way to kind of say this is that they have minimal surfaces in their homotopy classes with small principal curvatures, like bounded by epsilon, say. So that's, I mean, not the definition that's in the Calgary Marcus Neves paper. There are a lot of different ways to talk about how close you're being totally geodesic as a surface subgroup. But yeah, so what the definition that Calgary Marcus Neves make is of minimal surface entropy is as follows. Minimal surface entropy. And I'll go on the next page since it's kind of long to write, but there's a simple idea behind it. So yeah, so this is just going to be the limit as epsilon goes to 0. Limit log number of area less than 4 pi times L minus 1. Of surfaces pi and S epsilon of M. Right, so number of this set, size of this set, and then we divide this whole thing by L log L. Yeah, sorry, it doesn't quite fit on this line, but yeah, basically, so we are what we're doing here is, okay, so what the area of an element of S epsilon of M is we just kind of take the infinite area over all surfaces that are in that homotopy class, right? And which we can realize by minimal surface by that Shane Yao and Saxon conducted. So we're just counting area minimizing minimal surfaces, right? Area smaller than some number and that are kind of close to being totally geodesic. And that's going to grow exponentially by work that kind of Markovich did. That's how we know kind of this is growing exponentially. There are lots of these surfaces, like this, that's S epsilon of M are empty. That's due to kind of Markovich. And we know kind of the course rate of growth, which is like L log L, and so we divide by that. And sending epsilon to 0, we're just able to get a number out of this. So this is kind of their minimal surface entropy, and there's kind of a similar quantity that you have for counting geodesics that this is defined in analogy to. All right, so I'll say the theorem that I prove joined with Andre Neves, while also kind of saying the theorem that Collier-Marcus-Neves proved. Okay, so the theorem that we proved. So this is where we're going to start talking about scalar curvature, right? So scalar curvature is just an average of the sectional curvatures, so it's the number at each point that's telling you kind of how large metric balls of very small radius are. And so kind of Taylor expanding the volume of metric balls of radius r and r, you sort of kind of the first interesting term you get will like the first couple terms will be like what you'd have for Euclidean space, but the first interesting term you get will be will have curvature in it. And so basically the kind of the scalar curvature is just you get this curvature term, and it ends up just by matching up with what like the model constant curvature spaces are, you can just say that the scalar curvature is exactly what it should be based on what kind of the volumes of small metric balls and like the constant curvature, hyperbolic, and like I don't know, spherical spaces are. So scalar curvature is just number at each point, is just the average of all the sectional curvatures through all the tangent two planes to n. Right, so if we have scalar curvature at least -6, okay, so -6 is the scalar curvature of the hyperbolic metric, so we're kind of comparing against that. Then what we're able to prove is that our minimal surface entropy is smaller than the hyperbolic metric, and that of the hyperbolic metric, with equality only if we're isometric to the hyperbolic metric. Okay, so that's our theorem, and then I'll just in parentheses say the thing that like Collier-Marcus-Neves proved. So they, instead of a scalar curvature lower bound, they have a sectional curvature upper bound of -1. I'll say k less than equal to -1, and they get the inequality in the opposite direction. Okay, and so yes, we have this inequality, and we also prove rigidity in the case of equality, just like they do, but with kind of inequalities in opposite directions and an assumption on scalar curvature instead of sectional curvature. Right, so we don't have time to talk about their proof. It's a little different. Uses the Radner-Shaw theorem that I said before in kind of a creative way to prove the rigidity case. So I'll, so that's the kind of really original idea to kind of prove rigidity results with minimal surfaces using dynamical kind of methods. So that's one of the really cool things in their paper. But for us, right, so we have scalar curvature lower bound, and yeah, and so this is like some kind of comparison result for scalar curvature, kind of fixing the topology of the background manifold that everything's happening in, where we're looking at kind of areas of almost of surfaces that are homotopic to almost totally geodesic surfaces in the hyperbolic metric, areas of those surfaces. Yeah, and so in the remaining time, I just want to talk about the proof of this, but in kind of the special case that that M does not have any conformally flat infinitesimal deformations. Emits no infinitesimal conformally flat deformations. So what this condition means, so there are examples of closed hyperbolic manifolds that satisfy this condition. I would imagine that a random closed hyperbolic three manifold, say like the Dunfield-Thurston model, would satisfy this condition, although I haven't checked that. Be interesting to check, I think. But right, so the point here is that in general, if you have a closed hyperbolic three manifold, that's of course the hyperbolic metric is of course a conformally flat metric on that, but in general, you'll have other conformally flat metrics in different conformal classes, which you can then solve the unilateral problem for and get constant scalar curvature metrics, right? So, I mean, sometimes the hyperbolic metric is like kind of unique conformally flat constant scalar curvature metric on your closed hyperbolic manifold, but sometimes it isn't, right? So we have this condition to rule out these other conformally flat constant scalar curvature metrics, which I'll talk about. Yeah, well, you'll see how that comes into play in the proof. So anything else I want to say? Right. Okay. So I'll just so the proof is going to be I mean we have some metric with scalar curvature at least -6, and then what we're going to do is we're going to kind of run Ricci flow, and then that'll up to scaling take us back to the hyperbolic metric after finding many surgeries, right? So using yeah, kind of Perlman's work and on geometrization, and yeah, the fact that Ricci flow takes us back to the constant curvature model metric. And so we're going to keep track of kind of how like different geometric quantities of interest are evolving, like scalar curvature and area, and then get what we want by like looking at kind of the convergence of the Ricci flow back to the hyperbolic metric. So that's kind of the outline for the proof. Right, so I'll just write down, this is the Ricci flow equation is just flowing in kind of the opposite direction of the Ricci tensor. Okay. And so the proof I'm gonna give actually is not of the theorem that I just said, but of a theorem that's like very related to it and that kind of has most of the ideas. And so you'll, yeah, kind of has the main idea. So really we're gonna look at the case where there's a totally geodesic surface in the hyperbolic metric. In right. And then what we're going to prove, this is what we're going to prove, is that if the scalar curvature of our metric is bigger than or equal to -6, scalar curvature of the hyperbolic metric, then the area of the homotopy class of sigma is at least what it is in the hyperbolic metric. And it's just a totally geodesic surface in the hyperbolic metric, and also rigidity in the case of equality. We won't really talk about that, but that'll just kind of come. That's not really the hard part. The inequality here is really the hard part. And so why is this related to the theorem that I just said in the previous page? So this theorem relates about areas of surfaces that are homotopic to like surfaces that are almost totally geodesic in the hyperbolic metric. And so kind of asymptotically, we're getting totally geodesic surfaces here. And so like, I guess to kind of see how the basic argument goes, it's enough to kind of check that the inequality that you would expect if this inequality were true is true for totally geodesic surfaces, which is kind of the limiting case of the surfaces you're considering here. So what's going to kind of happen is that, I mean, this inequality is going to be true for the general surface is sigma and S epsilon of m, but up to like up to an error that goes to 0 as epsilon goes to 0. So that kind of would be like a factor like 1 plus big O of epsilon in front of this or something. Yeah, so that's great. So from now on, we're going to focus on just this case of sigma being totally geodesic. Right. So back to Ricci flow. I want to normalize it so that just multiply it by some number each time t, so that we get we fix the area starting at g scaled such that the volume of g bar of t is the volume of the hyperbolic metric. Okay, so we're just going to kind of run Ricci flow, and then so we have some solution for at least some small time interval, and we can do Ricci flow surgery kind of, and after finding many surgeries, we won't have any more surgeries. So yeah, we get this like Ricci flow surgery, but we're just going to normalize it so that it has just multiply the metric solving the solution to Ricci flow by number at each point, so that it has this volume. All right, and so we're going to define a sigma t just to be the the minimum area of any surface sigma prime homotopy to sigma in the metric g hat of t. Okay, and then so one thing we can check by, realizing a sigma of t by minimal surface, and then there's a way you can just sort of differentiate a sigma of t by differentiating the area of the minimal surface, realizing a sigma of t in time. And there's a computation you can do to kind of write that in a nice way and get this ordinary differential inequality that a sigma is satisfying. So I won't write that down at all, but I'll just say that what you get is that, right, so if we assume for contradiction that our claim on the previous page is false, and that this inequality here, this inequality fails, and then we run reach each flow starting at g. So like kind of assume this doesn't work, and we have that this inequality is failing. Then we actually have that area in the hyperbolic metric, which is the constant, right? This is just a constant minus the area in the metric g hat of t is at least 1 over t to the 1/4. Okay, so kind of there's ordinary differential equation we can write down, and assuming that the inequality that we want to show is true, assuming it fails, assuming kind of this inequality is written in red, then you get this inequality here by solving OD. But on the other hand, right, but okay, but right, the area of the totally geodesic surface in the hyperbolic metric, subtract this, we end up having the following inequality. Sorry, I'll just write this t to the minus 1/4. It'll just make more sense. This is bounded above by t to some number omega divided by 4. Okay, and so we have this other inequality. What this is coming from is, we're using Ricci flow surgery asymptotically takes us back to the hyperbolic metric after finding many surgeries. And one thing you have to check is that this inequality here that comes from like an ordinary differential inequality that like Ricci flows, the surgeries don't mess us up at all, but that ends up being fine. But on the other hand, you kind of know for large t, you're close to the hyperbolic metric, and you know kind of by linearizing, the Ricci flow at the hyperbolic metric, you kind of get this kind of stability analysis there. You get that the metric is converging back to a t bar of g hat of t is converging back to the hyperbolic metric fast enough that just kind of comparing what the area form of the two surfaces is based on like how close the metrics are, you can get this inequality. Okay, and I haven't said what omega is, so a priori there's kind of this Bachner formula that you kind of use, and after linearizing the Ricci flow of the hyperbolic metric, around this Bachner formula, and there's like spectral gap you have that tells you that omega is less than or equal to -1. And so to get a contradiction here, it's enough to show that omega is actually strictly less than -1, right? So yeah, so I'll just write that, that it's enough to show that omega is strictly less than -1. Okay, then this will be a contradiction, right? Like these two inequalities will contradict each other. Okay. But this kind of this like initial assumption we made on there being no infinitesimal conformally flat deformations actually ends up meaning that omega has to be strictly less than -1. So what happens? So this is, I'll end my talk after this, but I'll just kind of explain what why we have this like strict inequality in the case that there are no infinitesimal conformally flat deformations. So what happens is if we just kind of like write down the linearized Ricci flow and say, okay, so what happens if like the bottom like eigentensor or whatever is symmetric 2, 0 eigentensor has eigenvalue -1. So what happens then? Then you can just sort of you get this, the eigentensor has to kind of be it's called a Cauchy tensor, so kind of satisfies this nice condition. It's covariant derivative that is similar to what the second fundamental form of a surface would satisfy. And it's trace free, so it's in divergence free, so you kind of get all these conditions it satisfies. And it turns out that there's this right, so this is kind of like Hodge theory for conformally flat deformations, where if you kind of like all of the tangent vectors that are infinitesimal conformally flat deformations of the hyperbolic metric, I mean, these can be kind of written as classes of symmetric 2, 0 tensors, like some cohomology class of those. And there's like a Hodge theory where kind of your harmonic 2, 0 tensors that are parameterizing infinitesimal conformally flat deformations end up being exactly these 2, 0 tensors that I described that you have if you just kind of, if the bottom eigenvalue is -1, or really I guess top eigenvalue, since it's the spectrum is kind of negative and how I've set it up. But right, and so yeah, so it turns out if you kind of have like any kind of bottom eigentensor here with eigenvalue -1 would give you an infinitesimal conformally flat deformation. So kind of what this means, kind of Ricci flow is that like these kind of conformally flat deformations, if you like run for conformally flat metrics, if you kind of run Ricci flow on those, it's sort of not converging back to the hyperbolic metric fast enough for this argument to work. But there are all these examples of closed hyperbolic manifolds that have no infinitesimal conformally flat deformation, since like kind of, yeah, these like possible harmonic like symmetric 2, 0 tensors that you can have that parameterize the infinitesimal conformally flat deformations, and that are like the bottom eigentensors for this. When the eigenvalue is -1, there's kind of this different perspective on all that, where I mean the conformally flat structures, you can just kind of talk about like the holonomy of those is like maps from like pi1 of m into S0401, and so just kind of computing like this cohomology group of pi1 of m with coefficients in like the Lie algebra of S0401 will tell you what all your what your like kind of tangent space in the space of conformally flat structures is, so what all the infinitesimal conformally flat deformations are that you can do. And so you can just kind of compute this cohomology in some cases. And Kapovich does this for some for some kind of for surgeries on like certain knots, and then proves explicit examples where you have this condition is satisfied. And yeah, and so finally, I guess I'll just say that I mean, in the case that omega is equal to -1, you still kind of get this theorem that I said, but the argument is a little the theorem that I stated that's strong with Henry-Neves, but the argument is more subtle, and you have to really look at what kind of like finer information about what's happening with the convergence back to the hyperbolic metric, than kind of what's contained in the two inequalities that I wrote here. But you can still kind of work harder and get a contradiction in that case too, even if you have these infinitesimal conformally flat deformations. So yeah, so thanks for listening to my talk. I'll end it here. Thanks again to the organizers, and cool. So